Hello and welcome. If you're hearing my voice right now, you've come to the perfect place. Whether you're settling into your bed after a long day, lying down for an afternoon rest, or simply seeking a moment of peace in this busy world, you're exactly where you need to be. Tonight, we're going to travel through space and time together. We'll visit the most distant corners of the universe, witness the birth of stars, and explore mysteries that have puzzled scientists for generations. But we're going to do it in a way that allows your mind to relax, your breathing to slow, and your body to gently drift towards sleep. Before we begin our cosmic voyage, I want to invite you to become part of our community. If you enjoy falling asleep to stories about the wonders of science and the universe, please take a moment to like this video, subscribe to Sleepy Science Tales so you never miss a journey, and if you know someone who struggles to fall asleep, or who loves learning about the cosmos, share this with them. You'll be giving them the gift of peaceful, educational rest. Now, let your body sink deeper into your bed. Feel the weight of your head on the pillow. Let your shoulders drop. Release any tension you're holding in your jaw, your neck, your hands. Take a slow, deep breath in, and let it out even more slowly. Perfect. Tonight's journey begins 1 million miles from Earth, where a telescope floats in the darkness of space. This telescope has changed everything we thought we knew about the universe. Over the next few hours, I'm going to share with you the most remarkable discoveries ever made about our cosmos. Galaxies that shouldn't exist, black holes that grew impossibly fast, distant worlds where diamonds might rain from the sky, and evidence that forces scientists to question whether our entire understanding of reality needs to be rewritten. But don't worry about remembering every detail. This isn't a test. This is simply a journey. Let the words wash over you like gentle waves. If you drift away into sleep, that's perfect. If you stay with me until the end, that's wonderful too. There's no right or wrong way to experience this, so close your eyes if you haven't already. Get comfortable. Adjust your pillow one last time. And let's begin our journey. To the edge of time itself, floating silently through the void, 1 million miles from Earth, there exists a machine unlike any other humanity has ever built, the James Webb Space Telescope. A marvel of engineering and ambition, represents 30 years of planning, innovation, and hope. Imagine for a moment this delicate instrument. Its golden mirror, composed of 18 hexagonal segments, spans more than 20 feet across. Each segment is coated with a microscopically thin layer of gold, giving the telescope its distinctive appearance. Gold was chosen because it reflects infrared light with remarkable efficiency, and infrared light is the key to Webb's extraordinary vision. The telescope doesn't orbit Earth like its predecessor, Hubble. Instead, it resides at a special point in space called Lagrange Point 2, a location where the gravitational forces of Earth and the Sun balance perfectly. Here, shielded from the Sun's heat by a tennis court-sized sun shield, Webb's instruments remain incredibly cold, some approaching minus 400 degrees Fahrenheit. This extreme cold is essential, allowing the telescope to detect the faint infrared whispers from the most distant objects in the universe. When we look at distant objects in space, we're not just seeing across distance, we're looking backward through time. Light travels fast, approximately 186,000 miles every single second. But the universe is unimaginably vast. The light from distant galaxies has been traveling toward us for billions of years. When that light finally reaches the James Webb Space Telescope, it carries information about what those galaxies looked like billions of years ago. This is the remarkable thing. The telescope isn't just showing us faraway places, it's showing us the ancient past, the early universe, the cosmic dawn when stars first ignited and galaxies first formed. Scientists thought they knew what to expect when Webb opened its golden eyes. They had models, predictions, theories built over decades of careful observation and mathematical calculation. The early universe, they believed, would be primitive, chaotic, filled with small, irregular clumps of matter slowly organizing themselves into the magnificent structures we see today. They were wrong. Almost immediately after beginning its scientific observations, Webb revealed something shocking. The early universe was far more sophisticated, far more organized, far more mature than anyone had imagined possible. Let your breathing slow as you consider this. The universe, keeping secrets for 13 billion years, finally revealing itself to curious minds, showing us that reality is stranger and more wonderful than our best theories predicted. Webb's instruments can capture light from objects so distant that the universe was only a few 100 million years old when that light began its journey. The cosmic microwave background, the afterglow of the Big Bang itself, set out on its journey when the universe was only 380,000 years old. Now, Webb is filling in the gap, showing us what happened after that initial flash, during the time when darkness slowly gave way to light, and what it found has shaken the foundations of cosmology. Take another slow breath. Feel yourself relaxing deeper. The universe is vast, ancient, mysterious, and you're here, in this moment, learning its secrets as you drift gently towards sleep. Let's explore what Webb discovered, beginning with galaxies that should not exist. In the standard model of cosmology, the story we've told ourselves about how the universe evolved. There was supposed to be a natural order to things, a gradual progression from simple to complex, from chaos to structure. After the Big Bang, the universe was almost perfectly smooth, a hot, dense soup of particles expanding and cooling. Gravity, patient and persistent, would slowly pull matter together. Small clumps would form first. These would merge into larger clumps. Eventually, over hundreds of millions of years, the first true galaxies would emerge. These first galaxies were supposed to be small, messy, irregular. Think of them as cosmic toddlers, stumbling, disorganized, still learning how to walk. They would collide with each other, merge together, and slowly, over billions of years, organize into the grand spiral and elliptical structures we see in the modern universe. Our own Milky Way galaxy is magnificent, a spiral structure stretching 100,000 light-years across, containing hundreds of billions of stars, all organized into graceful curving arms. This beauty took time to develop, roughly 10 billion years of gradual assembly, mergers, and organization. So, when astronomers pointed the James Webb Space Telescope at the early universe, expecting to find cosmic toddlers, you can imagine their surprise when they found adults. Let me tell you about a galaxy named after a sacred river in the Himalayas. This galaxy exists in Webb's observations as it appeared just 290 million years after the Big Bang. The universe at that moment was only 2% of its current age. If the universe's entire history were compressed into a single year, this galaxy appeared on January 7th. What did scientists find? A fully formed galaxy, bright, chemically complex, already organized into a structured disk, containing enough material to form 10 billion stars like our Sun. And here's what makes this truly extraordinary. Its light reveals the presence of oxygen. Let your mind rest on that word for a moment. Oxygen. You're breathing oxygen right now. Every breath you take brings oxygen molecules into your lungs. This oxygen didn't exist at the beginning of the universe. The Big Bang created only the lightest elements: hydrogen, helium, and trace amounts of lithium. That's all. Everything else, every atom of carbon in your body, every molecule of oxygen in the air, every bit of iron in your blood, was forged inside stars. Stars are cosmic factories. In their cores, nuclear fusion creates heavier elements. When massive stars explode as supernovae, they scatter these elements into space, enriching the cosmic environment. For a galaxy to contain significant oxygen, stars must have already lived and died, multiple generations of them. The presence of oxygen is proof of stellar cycles: birth, life, death, and rebirth. This galaxy accomplished in a few 100 million years what should have taken billions. It's as if you expected to find an infant, but instead discovered a fully grown adult. The team that discovered this used an extraordinary amount of telescope time. 9 days of continuous observation focused on a patch of sky so small that if you held a grain of sand at arm's length, it would cover the entire area. And in that tiny patch of sky, they found something that breaks nearly every rule of early universe formation. Close your eyes and picture this. Imagine the early universe, dark, mostly empty, slowly awakening, and there, shining brightly, a fully formed galaxy already mature beyond its years. A cosmic mystery floating in the darkness. The implications ripple outward. If such a mature galaxy exists in such a tiny random sample of sky, how many more must be out there? The mathematics suggests there should be many, and that terrifies cosmologists, because their models don't allow for rapid assembly on this scale. Either stars formed and died much faster than believed possible, or something about our understanding of the early universe is fundamentally wrong. Let your breathing deepen. Feel the weight of these cosmic mysteries, not as a burden, but as a wonder. The universe is larger and stranger than we knew, and that's beautiful. But this galaxy is not alone. Scattered throughout Webb's observations, scientists found hundreds of mysterious objects, tiny red points of light, objects so strange that for 3 years, no one could explain what they were. Let's explore these enigmatic little red dots and discover what they might reveal about the birth of black holes. Breathe slowly, in and out. We're going to explore something mysterious now, something that appeared in nearly every deep image the James Webb Space Telescope captured. Scientists called them little red dots. Imagine you're looking at images of the distant universe. The frame is filled with galaxies. Spirals, ellipticals, irregular shapes, all glowing with the light of billions of stars. But scattered throughout, you notice small, compact, bright red points, not galaxies, not stars. Something else entirely. At first, researchers assumed they were distant, ancient galaxies. Old galaxies tend to appear red because their stars have aged. But something didn't fit. These objects were too small, too compact. If they were galaxies with enough stars to explain their brightness, those stars would need to be packed together at impossible densities. Another possibility emerged. Perhaps these weren't galaxies full of stars, but single supermassive black holes. When black holes feed on surrounding gas, they can outshine entire galaxies. The matter spiraling inward gets compressed and heated to millions of degrees, creating tremendous amounts of radiation. But this explanation had its own problem. Active black holes that bright should blast out X-rays and radio waves. Scientists searched for those signals. They found almost nothing. The little red dots were too quiet to be typical active black holes, yet too bright to be normal galaxies. For 3 years, the mystery deepened. Hundreds of these objects appeared in observations of the early universe, from around 400 million to 1 billion years after the Big Bang. Then mysteriously, they seemed to vanish from later cosmic epochs. Let yourself sink deeper into your pillow as I tell you what scientists finally discovered. In 2025, researchers at the University of Copenhagen announced their conclusion. After years of careful analysis, the little red dots are young black holes, but not ordinary ones. These black holes are wrapped in dense cocoons of glowing ionized gas. They're actively consuming that gas, growing rapidly, generating enormous heat that shines through the cocoon. The radiation passing through the gas gives them their distinctive red color. Think of it like a cosmic chrysalis. Inside, something is transforming. These aren't the giant supermassive black holes we find in modern galaxies. They're younger, hungrier, still in their growth phase. We might be witnessing the birth of the monsters that will one day anchor every major galaxy. But some scientists think the truth is even stranger. They propose these objects might be something never seen before. Black hole stars. The concept sounds like science fiction, but follow the logic gently, letting the ideas wash over you. Imagine a black hole sitting at the center of an enormous sphere of hot, dense gas. The black hole pulls matter inward. As gas falls toward the event horizon, it accelerates, compresses, heats up. This releases staggering amounts of energy. Here, single quote says the key. Only a tiny fraction of the infalling gas actually crosses the event horizon and disappears forever. Most of it gets blasted back out. The intense radiation pushes the majority of the material away before it can be swallowed. Black holes, scientists sometimes say, are messy eaters. The rejected gas forms a dense, turbulent atmosphere surrounding the black hole. From a distance, this entire structure, The black hole plus its gas envelope looks like a single gigantic star, except it's not powered by nuclear fusion like normal stars. It's powered by gravity, by the violent compression of infalling matter. One little red dot analyzed in detail appeared to have so much atmosphere that it couldn't be explained as a collection of ordinary stars. It seemed to be one gigantic, relatively cool star, but with tremendous heat raging at its core. If black hole stars truly exist, they might solve one of cosmology's greatest puzzles. Astronomers have long wondered how supermassive black holes grew so massive so quickly. Normal feeding processes should take billions of years, yet we find billion solar mass black holes existing less than 1 billion years after the Big Bang. The mathematics doesn't work. Black hole stars might be the answer. If young black holes can wrap themselves in dense gas cocoons, they can feed much faster than exposed black holes. The cocoon shields the growing black hole from its own radiation, allowing it to consume material more efficiently. Over several 100 million years, it could balloon from a modest seed into a cosmic giant. This would explain why little red dots appear everywhere in the early universe, but vanish about 1 billion years after the Big Bang. They represent a temporary phase of black hole growth. Eventually, the cocoon gets consumed or blown away. The feeding frenzy ends. What remains is a mature supermassive black hole sitting quietly at the center of a galaxy. Breathe slowly. Let these cosmic mysteries drift through your mind like clouds across a night sky. Black holes, wrapped in glowing gas, feeding furiously in the early universe, growing into the monsters that would shape galaxies for billions of years. But even setting aside these little red dots, Webb found something else troubling. Galaxies that are simply too big, too massive, growing faster than physics should allow. Let the weight of your body press into the mattress. Let your muscles relax completely, and listen as I tell you about the universe's impossible growth spurt. There was supposed to be a speed limit, not for light. We've known about that for over a century. But a speed limit for growth, for structure formation, for how quickly the universe could organize itself from primordial chaos into galaxies, stars and planets. Gravity operates at a fixed strength. The universe was expanding, working against gravity's pull. Dark matter would clump together first, forming invisible halos. Normal matter would fall into these halos. Gas would collect, compress, heat up. Eventually stars would ignite. Gradually, over hundreds of millions of years, the earliest galaxies would assemble. The key word is gradually. According to calculations refined over decades, the first billion years should have produced small, faint, chaotic structures. Finding anything as bright and organized as modern galaxies should have been impossible. The James Webb Space Telescope disagreed. In its first year of observations, Webb found bright galaxies everywhere in the early universe. Not just a few anomalies, a consistent population of objects that challenged expectations. Some appeared as luminous as mature galaxies despite existing when the universe was only 3% of its current age. Let your mind rest gently on this image. The early universe, not dark and primitive as expected, but blazing with galaxies, structures assembling at impossible speed, cosmic evolution running in fast forward. Scientists checked and rechecked their measurements. They scrutinized the telescope's calibration. They verified distance estimates. The results held. These galaxies truly existed in the early universe, and they truly were far larger and brighter than models predicted. One particularly dramatic example appeared as it existed just for 100 million years after the Big Bang. It contained billions of stars worth of material. Our own Milky Way took over 13 billion years to assemble its hundreds of billions of stars. How can a galaxy accumulate so much material so quickly? Several explanations have been proposed. Perhaps star formation was more efficient in the early universe. Perhaps the first stars were more massive and luminous, making young galaxies appear brighter than their actual mass would suggest. Perhaps dark matter behaved differently in the distant past. Each explanation has problems. Higher star formation efficiency requires conditions we don't observe elsewhere. More massive early stars would leave distinct chemical signatures we haven't found. Modified dark matter would conflict with other observations. Let your breathing slow even further. Feel the gentle rise and fall of your chest. The mystery deepens. But that's all right. Not all mysteries need immediate solutions. Sometimes it's enough to simply wonder. The universe produced large, bright, mature galaxies far faster than our models allow. Either something accelerated growth in ways we don't understand, or our models are missing something fundamental. And this crisis extends beyond galaxies themselves. The same observations that revealed impossibly massive galaxies also revealed something even more disturbing. Supermassive black holes that dwarf their host galaxies. Objects so oversized that they break a relationship astronomers thought was universal. In the nearby universe, there's a pattern. The mass of a galaxy's central supermassive black hole scales predictably with the mass of the galaxy itself. Bigger galaxies have bigger black holes. The ratio is remarkably consistent. For every 1,000 units of stellar mass, there's roughly 1 unit of black hole mass. This relationship suggests galaxies and their black holes grow together, evolving in lockstep over cosmic time. An elegant dance. A cosmic partnership. In the early universe, the partnership is broken. Webb's observations revealed supermassive black holes that are dramatically oversized. Instead of a 1,000-to-1 ratio between stellar mass and black hole mass, researchers found ratios of 100-to-1, sometimes 10-to-1. In extreme cases, the black hole mass equaled the total stellar mass of its host galaxy. These black holes aren't slightly larger than expected. They're 10 to 100 times more massive than the relationship predicts. Close your eyes and imagine this. A young galaxy, still forming, still gathering stars. And at its center, a black hole already grown to monstrous proportions. A cosmic imbalance. A violation of the expected order. How did these black holes grow so large while their galaxy stayed small? One explanation involves timing. Perhaps in the early universe, black holes grew first and galaxies assembled later. The black holes consumed available gas before stars could form, keeping galaxies small while the black holes ballooned. But this raises a profound question. What created such massive black hole seeds in the first place? Normal stellar collapse produces black holes of perhaps a few dozen solar masses. Growing from there to millions or billions of solar masses through feeding alone would take longer than the universe's age at that time. Some researchers proposed that the first black holes formed through direct collapse. Instead of starting as stellar remnants, they emerged when enormous gas clouds collapsed directly into black holes, without ever becoming stars. This would create heavy seeds, perhaps 100,000 solar masses or more, giving the black holes a head start. Let your mind drift with this idea. Massive clouds of pristine gas in the early universe, collapsing not into stars but directly into black holes. Cosmic shortcuts creating the seeds of monsters. If heavy seeds are real, there should be a population of intermediate objects between the primordial seeds and the monsters we observe. The telescope continues searching. Each observation pushes deeper into cosmic history. But among these impossible objects, scientists found one that defied every limit. A black hole eating faster than physics allows. Actually, let me correct that. They thought they found such an object. The story of this discovery and correction is worth telling, because it reveals something important about how science works. Breathe deeply. Let tension flow out of your body with each exhale, and listen to this tale of cosmic feeding frenzies, and the importance of careful measurement. As you sink deeper into comfort, deeper into relaxation, let me tell you about something that affects every corner of the cosmos, something invisible, mysterious, and absolutely fundamental to the nature of reality itself. Dark energy. The universe is expanding. This isn't controversial. Since the 1920s, when astronomer Edwin Hubble first measured the recession of distant galaxies, we've known that space itself is stretching. Every galaxy, except our nearest neighbors, is moving away from us. The farther away they are, the faster they recede. But here's where it gets interesting and strange. The expansion isn't slowing down, as gravity should cause it to. The expansion is accelerating. Galaxies are flying apart faster and faster, as if some invisible force is pushing them. We call this mysterious force dark energy, though that name is really just an admission of our ignorance. We don't know what it is. We don't know why it exists. We only know that it's there, and it makes up roughly 68% of everything in the universe. Let your breathing slow as you contemplate this. More than 2/3 of everything that exists is something we don't understand at all. Something invisible. Something that only reveals itself through its effect on the expansion of space. For decades, scientists assumed dark energy was constant, a fixed value woven into the fabric of space-time itself, a cosmological constant, as Einstein once called it. This assumption made the mathematics tractable. It allowed cosmologists to build predictive models, and for the most part, it worked well. But the James Webb Space Telescope, combined with other observations, has revealed something troubling. Dark energy might not be constant after all. Data from multiple surveys suggest that dark energy has weakened over the past 4 to 5 billion years. If true, this discovery would overturn one of the foundational assumptions of modern cosmology. Breathe in slowly, hold for a moment, and release. Let this mystery settle gently in your mind like snow falling on a quiet landscape. The evidence comes from measuring the expansion history of the universe with unprecedented precision. By observing how galaxies cluster at different distances, astronomers can reconstruct how fast space expanded at various epochs. The results show a curious pattern. The expansion rate in the distant past matches predictions reasonably well. But in the more recent universe, something seems off. The expansion isn't accelerating as uniformly as the constant dark energy model predicts. One interpretation is that dark energy had greater strength in the past and has been gradually declining. The universe's acceleration is slowing down. Close your eyes and picture this. If you haven't already, imagine the universe as a vast ocean, waves of space-time rippling outward from the Big Bang, carrying galaxies like boats on an expanding sea, and the wind pushing those boats, the dark energy gradually weakening, the acceleration easing. If dark energy continues to weaken, the implications are profound. The accelerating expansion could eventually stop. The universe might coast forward at a steady rate, or depending on how dark energy evolves, expansion could even reverse. Some researchers have speculated about extreme scenarios. A weakening dark energy could lead to a big crunch, where the universe collapses back on itself, all matter and energy converging to a single point, the opposite of the Big Bang. Or it could transition to a big rip, where the decay of dark energy leads to increasingly violent expansion that eventually tears apart galaxies, stars, atoms, everything. But don't let these dramatic scenarios disturb your rest. These are distant futures, trillions of years away if they happen at all. For now, they're simply interesting possibilities, thought experiments, ways of exploring what the universe might become. Let your body relax completely. Feel the mattress supporting you. Feel gravity, that other mysterious force, gently holding you against the Earth. The current data show only hints of variation in dark energy, not definitive proof. The uncertainties are large. More observations are needed. But the mere possibility that dark energy isn't constant represents a fundamental shift in cosmological thinking. For decades, physicists assumed the universe had a fixed accelerator pedal. Dark energy pushed expansion faster and faster forever. The ultimate fate of the cosmos was isolation, as galaxies receded beyond each other's horizons into eternal darkness. A cold, lonely end. A variable dark energy changes this picture completely. The future becomes uncertain in ways it never was before. And uncertainty, while uncomfortable for those seeking definitive answers, is the seedbed of discovery. The James Webb Space Telescope contributes to this story indirectly. Its observations of unexpectedly mature galaxies in the early universe challenge timelines that assume constant dark energy. If dark energy was stronger or behaved differently in the early cosmos, it could explain some of the anomalies. The two large galaxies, the two massive black holes, the accelerated evolution. Everything connects. The Hubble tension, which I'll explain in a moment. The massive early galaxies, the variable dark energy, these aren't separate puzzles. They're facets of a single deeper mystery about the nature of space, time, and energy. Breathe deeply. Let the oxygen fill your lungs. Feel your chest rise and fall. The rhythm of breath, the rhythm of cosmic expansion, both following patterns we're only beginning to understand. Now let me tell you about the Hubble tension, a disagreement so significant that it might herald a crisis in cosmology. There are two main ways to measure how fast the universe is expanding. The first involves observing objects in the nearby universe. Astronomers identify stars with known intrinsic brightness, measure how bright they appear, and calculate their distance. By combining distances with recession velocities, they determine how fast space is expanding locally. The second method involves observing the cosmic microwave background, the afterglow of the Big Bang. This radiation carries information about the early universe. By analyzing its properties and applying the standard cosmological model, scientists can predict what the expansion rate should be. These two methods should give the same answer. They don't. The nearby universe measurements consistently find expansion rates around 73 kilometers per second, per megaparsec. Don't worry about the units. Just know it's a specific number. The cosmic microwave background predictions give around 67 kilometers per second per megaparsec. The difference might seem small, but it's far larger than the measurement uncertainties allow. Both methods have been refined repeatedly over decades. The discrepancy persists. It even grows slightly as measurements improve. Some astronomers hoped the tension was caused by measurement errors. Perhaps previous telescopes couldn't resolve individual stars clearly enough. Perhaps overlapping stars introduced systematic errors. The James Webb Space Telescope eliminated this hope. Its resolution is dramatically sharper than any previous instrument. When researchers reanalyzed the distance measurements using Webb's data, they found the previous results were correct. The expansion rate measured in the nearby universe remains around 73. The tension is real. Let this sink in slowly, gently, as you sink deeper into your pillow. The universe is expanding faster than our best model predicts. Something is missing from our understanding. Either something is wrong with our measurements of the cosmic microwave background, or something is wrong with our cosmological model, or both. The standard model of cosmology, called lambda CDM, has explained observations successfully for decades, but it predicts an expansion rate around 67. The universe appears to be expanding faster than this model allows. What could explain this discrepancy? Several solutions have been proposed. Perhaps the early universe contained an additional component of energy that boosted expansion temporarily. Perhaps dark energy behaves differently than assumed. Perhaps new physics is required. Modifications to general relativity on cosmological scales, or exotic particles we haven't discovered yet. One intriguing idea keeps appearing in discussions. Early dark energy. What if there was extra dark energy in the early universe? Not the constant dark energy we observe today, but a temporary additional component that existed only during the first few 100 million years, then faded away. This early dark energy would have pushed the universe apart faster during its infancy. It would have stretched space more quickly than the standard model assumes. This accelerated early expansion would have several effects. It would change the balance of cosmological parameters. The seeds of structure formation would be slightly larger. Dark matter halos would grow faster. Galaxies would form earlier and brighter. A team of physicists from MIT tested this idea using sophisticated computer simulations. They incorporated a model of early dark energy and asked what it would do to galaxy formation. The results were striking. With early dark energy, galaxies form earlier and shine more brightly. The model predicted exactly what the James Webb Space Telescope observed: bright, massive galaxies appearing much sooner than standard cosmology allows. One researcher described the finding as potentially a unified solution to major issues facing cosmology. If observational findings from the telescope continue to hold, this might be evidence for early dark energy's existence. The proposal is elegant, A single modification to cosmology could resolve two separate puzzles, the Hubble tension and the impossibly bright early galaxies. This is how physics often progresses. Unexplained phenomena accumulate until someone identifies the deeper principle that connects them. But early dark energy remains controversial. Not all physicists are convinced. Some argue the evidence is circumstantial. Others point out that early dark energy creates tensions with other observations. The debate continues. More data are needed. The James Webb Space Telescope keeps observing, adding to the evidence on all sides. Let your mind drift with these cosmic currents. Dark energy, expanding space, mysteries within mysteries, questions leading to deeper questions. What seems increasingly clear is that our understanding of the universe is incomplete. The standard model has served us well for decades, but it may be reaching its limits. The anomalies are multiplying faster than explanations. And in the midst of these cosmic mysteries, the telescope found something so dramatic, so undeniable, that its very existence validated 50 years of theoretical predictions. A supermassive black hole, ejected from its own galaxy, racing through space faster than almost any object ever observed. Let your breathing deepen. Feel yourself becoming heavier, more relaxed. And listen as I tell you about a cosmic exile, a monster cast out into darkness, leaving a trail of newborn stars in its wake. Something enormous is tearing through space. A supermassive black hole weighing 20 million times the mass of our Sun, moving at 2.2 million miles per hour, trailing a 200,000 light-year wake of newborn stars behind it. Let those numbers wash over you gently. Don't try to grasp their full magnitude. Just feel their weight, their immensity, like standing at the base of a mountain and looking up. This isn't science fiction. This is confirmed observation. The James Webb Space Telescope provided the definitive evidence. Scientists first noticed something strange in 2023 while examining images from the Hubble Space Telescope. They saw a thin line extending from the center of a distant galaxy. At first, they thought it might be an artifact, a glitch in the camera, a cosmic ray strike. But the line persisted in multiple observations. It was real, and it was connected to the galaxy's core. The team hypothesized they were seeing the wake of a runaway supermassive black hole, a black hole ejected from its galaxy, plowing through surrounding gas, compressing material ahead of it, leaving a trail of star formation behind. Skeptics offered alternative explanations. Perhaps it was a shredded dwarf galaxy. Perhaps an edge-on disk seen at just the right angle. The evidence was suggestive but not conclusive. Then the James Webb Space Telescope looked and provided proof. Using its near-infrared spectrograph, the telescope didn't just image the object. It measured motion. It analyzed how fast gas was moving at different points along the structure, and what it found removed all doubt. At the tip of the feature, there's a sharp velocity change. Gas suddenly jumps by roughly 600 kilometers per second over a very short distance. This kind of abrupt change can only be caused by one thing: a supersonic bow shock. Something massive is pushing through the gas faster than sound waves can travel. It's compressing material in front of it, creating a shock front. Behind the shock, gas cools and collapses, forming new stars that stream out in a long tail. Close your eyes and imagine this: a black hole, invisible itself, but revealed by its effect on everything around it, plowing through intergalactic space like a ship through water, leaving a glowing wake of creation behind it. The researchers calculated the black hole's velocity from the shock data, roughly 2.2 million miles per hour. For perspective, Earth orbits the Sun at about 67,000 miles per hour. This black hole is moving more than 30 times faster. At this speed, the black hole will escape its galaxy entirely. It will never return. It will wander through intergalactic space forever, a cosmic exile. But how does something with the mass of 20 million suns get ejected from a galaxy? Let your breathing slow as I explain the two mechanisms that can produce such enormous velocities. Both require extraordinary violence. The first involves a three-body interaction. If three supermassive black holes end up in the same galactic core, their gravitational dance can slingshot one member out at tremendous speed. Imagine three massive objects orbiting each other, their paths becoming more chaotic with each pass, until finally one is flung outward with enough force to escape, while the other to remain behind, bound in a shrinking orbit. The second mechanism involves gravitational waves. When two supermassive black holes merge, they release enormous energy in ripples through space-time itself. If the merger is asymmetric, the burst of gravitational radiation can kick the newly formed black hole with enough force to escape the galaxy. The team analyzing this runaway believes the merger scenario is most likely. The black hole's mass and velocity match predictions for a gravitational wave recoil kick. This discovery validates 50 years of theoretical work. Scientists predicted runaway supermassive black holes decades ago, working out the mathematics, calculating the conditions, predicting what we might observe. Now, finally, we've seen one, and the galaxy left behind might have a strange future. A galaxy without a central supermassive black hole. We don't know what happens to such a system. We've never observed one. The central black hole plays an important role in galaxy evolution, regulating star formation, influencing the distribution of gas, anchoring the entire structure. What happens when that anchor is torn away? The runaway black hole didn't come from nowhere. Its origin lies in a spectacular cosmic collision, two galaxies crashing together, their supermassive black holes spiraling toward each other, and the violent aftermath that sent one monster flying into the void. The host system is called the Cosmic Owl. It earned this name because of how it looks. To ring galaxies approaching each other, their cores glowing brightly like a pair of eyes. The shape resembles an owl's face staring back at observers across billions of light years. Ring galaxies are already rare. They form when one galaxy punches through the center of another, sending ripples outward through the disk like a rock dropped in a pond. Finding two ring galaxies interacting with each other is extraordinary, but the Cosmic Owl contains something even more remarkable. That long linear feature extending from the system, the wake of the runaway supermassive black hole. Breathe deeply. Let your body relax. Picture this cosmic drama unfolding over millions of years. Galaxies drifting closer together, drawn by mutual gravity. Stars rarely colliding. Space is mostly empty, but the supermassive black holes at the galaxy centers sinking toward each other, orbiting closer and closer. Something triggered an ejection. Either a three-body interaction flung one black hole outward, or two black holes merged asymmetrically, and the resulting recoil kick propelled the combined object away. The ejected black hole carried enormous momentum. It blasted through the surrounding gas at supersonic speed, compressing material ahead of it into a brilliant bow shock. Behind it, the compressed and cooling gas collapsed into new stars, creating a trail more than 200,000 light-years long. 200,000 light-years. That's twice the diameter of our entire Milky Way galaxy. The weight behind this runaway black hole is twice as large as our entire cosmic home. Let that image rest gently in your mind. A trail of newborn stars, stretching across intergalactic space, marking the path of an invisible monster. A cosmic breadcrumb trail showing where the black hole has been. The James Webb observations captured the bow shock in unprecedented detail. The spectrum revealed signatures of fast radiative shocks and rapid cooling. The chemistry and velocity measurements matched predictions for a supersonic object. Plowing through diffuse gas. Everything points to one conclusion. A supermassive black hole was violently ejected from the Cosmic Owl and is now racing through space. Leaving creation in its wake, this discovery has profound implications. If runaway supermassive black holes are real, and this observation proves they are, there might be many more wandering through the universe. Some estimates suggest millions could be drifting through intergalactic space, invisible and undetectable unless they happen to pass through gas clouds dense enough to produce visible effects. The universe may be haunted by cosmic exiles, monsters roaming the darkness between galaxies, ancient black holes cast out long ago, now traveling alone through the void, occasionally leaving trails of star formation when they pass through tenuous gas. Imagine the loneliness. No, perhaps loneliness is the wrong word. Black holes don't feel. But imagine the solitude. a massive object that once sat at the center of a galaxy surrounded by billions of stars, orbited by planets and solar systems, now adrift in the emptiness between galaxies, where space is so vast and empty that it would take light millions of years to reach the nearest structure. And yet, even in exile, this black hole creates. The stars forming in its wake will live for billions of years. Planets might form around them. Life might one day emerge, all because a black hole, fleeing its home, compressed gas as it passed. Destruction and creation, intertwined. Violence giving birth to beauty. This is the nature of the cosmos. Let yourself sink deeper now. Let the story of the runaway black hole drift through your consciousness, like the object itself drifts through space, moving, always moving, but peacefully, silently, leaving light in its wake. But this raises questions about how supermassive black holes form in the first place. If they can be ejected, merged, flung across the universe, their history must be more violent and chaotic than we imagined. Understanding this violence requires understanding how black holes are born, and the answer might involve seeds for heavier than anyone expected. Now let's journey from the largest structures in the universe, those massive black holes and ancient galaxies, down to something much smaller but no less fascinating. Planets, worlds orbiting distant stars, some familiar, some strange beyond imagining. The James Webb Space Telescope has revealed worlds that challenge our understanding of what planets can be. Let me tell you about a planet where it might rain diamonds. 6,000 light years from Earth, the planet orbits a pulsar. A pulsar is a neutron star, a dead stellar remnant spinning dozens of times per second, beaming radiation across space like a cosmic lighthouse. These objects have the mass of our Sun compressed into a sphere the size of a city. The density is almost incomprehensible. A teaspoon of neutron star material would weigh about 1 billion tons on Earth. Not a pleasant place for a planet, yet planets can exist in these extreme environments. This particular planet has a mass comparable to Jupiter, making it a gas giant. But its atmosphere contains something no one expected. No water, no methane, no carbon dioxide, none of the familiar molecules we find in gas giants throughout our galaxy. Instead, its atmosphere is dominated by helium and molecular carbon. Pure carbon in forms designated C and C by chemists. These molecules are extremely unusual because at planetary temperatures, carbon normally bonds with other elements. Let your breathing slow as you picture this. A giant planet orbiting a dead star, its atmosphere glowing with pure carbon. Unlike any world in our solar system, unlike any world we've ever discovered, the planet is also misshapen. Gravitational forces from the nearby pulsar stretch it into a lemon shape. It completes a full orbit in under 8 hours, racing around its stellar companion at tremendous speed. The intense pressure inside this planet could cause remarkable transformations. Carbon under extreme compression crystallizes, and crystallized carbon is diamond. Scientists believe the carbon in this planet's atmosphere is sinking into the interior, where crushing pressures transform it into diamond crystals. These diamonds fall like rain, accumulating somewhere in the planet's depths. Diamond rain. Let that image settle gently in your imagination. Precious stones falling through an alien atmosphere, not as small gems but as a continuous precipitation. A treasure beyond measure in a place no one could ever reach. Diamond rain isn't entirely new to planetary science. Researchers have theorized it might occur deep inside Neptune and Uranus in our own solar system. But this distant world takes the concept to extremes. The mystery deepens when scientists try to explain how such a planet formed. Normal planets form from the disk of gas and dust surrounding young stars. They inherit the chemical composition of their birth cloud, which typically contains abundant hydrogen, oxygen, nitrogen, and other common elements. A planet with pure carbon and helium can't have formed this way. Pulsar planets are rare to begin with. Only a handful are known. They might form from the debris of the supernova that created the pulsar, or from material stripped from a companion star. But neither scenario easily produces the observed composition. One proposed explanation involves crystallization processes unique to cooling compact objects. As the interior cooled over billions of years, carbon and oxygen separated. Pure carbon crystals floated to the top and mixed into the helium atmosphere. The oxygen and nitrogen somehow stayed behind. The physics is speculative. No one fully understands this world. What seems clear is that planetary diversity extends far beyond our imagination. But strange planets aren't limited to exotic systems around dead stars. The telescope has found bizarre worlds much closer, in our cosmic neighborhood, including one that shouldn't have an atmosphere but somehow kept it. Let me tell you about a lava world. Some planets orbit so close to their stars that they should be airless. The intense radiation strips away any gases clinging to the surface. The stellar wind blasts particles into space. Over millions of years, the atmosphere evaporates completely, leaving bare rock behind. This is well-established physics. We've observed it countless times. Then Webb examined a planet called TOI 561b. This world orbits one of the oldest stars in the Milky Way, a star that formed roughly 10 billion years ago, when the universe was less than 4 billion years old. TOI 561b orbits so close that its year lasts less than 12 hours. At that distance, the dayside temperature exceeds 2,000 degrees Celsius. The surface is molten. A global ocean of magma covers the planet, glowing orange and red under perpetual stellar bombardment by every expectation. This world should be bare rock. 10 billion years of intense radiation should have stripped away any atmosphere long ago. But when astronomers measured the planet's temperature, something was wrong. The day side was cooler than predicted. Heat was being distributed away from the star-facing hemisphere. Somehow, something was transporting energy. The only explanation is an atmosphere. Close your eyes and picture this molten world, glowing red and orange, surface churning with liquid rock, and above it, surprisingly, a thick blanket of gases, persisting against all odds, defying the harsh radiation that should have destroyed it billions of years ago. One researcher described the planet as really like a wet lava ball. The atmosphere somehow persists, despite conditions that should have destroyed it. How is this possible? The leading theory involves continuous replenishment. The magma ocean constantly releases gases. Volcanic activity on a planetary scale pumps volatiles into the atmosphere, faster than stellar radiation can strip them away. This creates a dynamic equilibrium. The atmosphere is constantly being destroyed and constantly being rebuilt. It exists in a state of perpetual regeneration. Let your body relax as you contemplate this. A planet where the atmosphere is always dying and always being reborn. A cosmic phoenix rising again and again from molten stone. If magma oceans can sustain atmospheres even under extreme stellar bombardment, then the range of potentially interesting planets expands dramatically. Worlds we dismissed as airless might actually maintain thin but significant gas envelopes. This matters for the search for life. Atmospheres regulate temperature. They shield surfaces from radiation. They enable complex chemistry. A universe with more atmospheric planets is a universe with more possibilities. Though TOI 561b itself isn't habitable, its temperatures far exceed anything compatible with life as we know it. The discovery expands our understanding of where atmospheres can exist. And speaking of life, the telescope has examined worlds that might, just possibly, be capable of supporting it. Let your breathing deepen, relax further, and let me tell you about the search for signs of life on distant worlds, and the fierce debates these searches have sparked. Can the James Webb Space Telescope detect signs of life on distant worlds? This question has divided astronomers since the telescope began operations. The answer depends not just on the telescope's capabilities, but on what we mean by life, and how confidently we can interpret chemical signatures across interstellar distances. In 2025, a team of researchers made a dramatic announcement. They had found what they called the strongest evidence yet for potential biosignature, gases in the atmosphere of an exoplanet named K218b. The planet orbits a red dwarf star roughly 124 light-years from Earth. It's larger than Earth but smaller than Neptune, placing it in a category called sub-Neptunes. These worlds have no analog in our solar system, making them particularly mysterious. K218b sits in its star's habitable zone, where temperatures might allow liquid water to exist. Some researchers have proposed it could be a Hycean world, a planet covered by a global ocean beneath a thick hydrogen-rich atmosphere, using new transit spectra from Webb. The team announced they had detected signatures consistent with dimethyl sulfide and possibly dimethyl disulfide. On Earth, these gases are strongly associated with marine biology. Phytoplankton produce them in our oceans. The implication was electrifying. If these gases exist on K218b, and if they can't be produced by non-biological processes, they might indicate life. But the scientific community responded with intense skepticism. Let your breathing remain slow and steady as I explain the debate. This is important, not because we need to resolve it tonight, but because it reveals how science works. How carefully scientists must proceed when making extraordinary claims. Other researchers argued the signal was too weak to draw definitive conclusions. The data were noisy. The detection was at the edge of what the telescope could measure. Alternative explanations couldn't be ruled out. Critics also questioned the Hycean world concept itself. Some argued K2-18b might not be an ocean world at all, but a mini-Neptune with a thick atmosphere and no solid surface. Under those conditions, any biosignature interpretation would be meaningless. The debate highlighted the limits of current technology. Webb wasn't designed specifically for exoplanet atmospheres. It was conceived before the explosion of exoplanet discoveries. Now scientists are pushing it beyond its original specifications. Extracting signals from noise at the very edge of possibility, more observations are planned. Additional transits have been captured and await analysis. The data might eventually clarify whether dimethyl sulfide truly exists on K218b. But even if the detection is confirmed, proving biological origin will be extraordinarily difficult. We would need to demonstrate that no abiotic process could produce these gases. Given how little we know about exotic planetary chemistry, that bar may be impossible to clear with current knowledge. Some astronomers see value in the controversy regardless of outcome. As one researcher noted, if the result is that the public becomes more cautious about future claims of life detection, that wouldn't be a terrible thing. Science requires skepticism. K2-18b remains a high-value target for understanding sub-Neptune atmospheres. Whether or not it hosts life, studying its chemistry teaches us about planetary diversity and the range of conditions that exist in our galaxy. But there's another system that has captured even more attention. A system where 7 Earth-sized worlds orbit a dim red star, and where the telescope is actively searching for atmospheres on potentially habitable planets. Let me tell you about TRAPPIST-1.40 light-years away. 7 Earth-sized worlds orbit a cool red dwarf star. The TRAPPIST-1 system has captivated astronomers since its discovery in 2017. No other known system contains so many terrestrial planets packed so closely together. 3 of them orbit within the star's habitable zone, where liquid water might persist on their surfaces. Of these 3, TRAPPIST-1e has emerged as the most intriguing. Its size, mass, and density closely match Earth's. Its distance from its star allows moderate temperatures. If any world in this system could support an ocean, TRAPPIST-1e is the leading candidate. But there's a requirement. For liquid water to exist, the planet must have an atmosphere, without a blanket of gases to trap heat and regulate temperature. Any surface water would freeze or evaporate into space. Does TRAPPIST-1e have an atmosphere? The James Webb Space Telescope has been working to answer this question. The results so far are tantalizing but inconclusive. Let your mind drift gently as I explain the technique. When TRAPPIST-1e passes in front of its star from our perspective, an event called a transit, some of the starlight filters through the planet's atmosphere before reaching us. If gases are present, they absorb specific wavelengths, leaving telltale signatures in the spectrum. The initial observations ruled out several possibilities. TRAPPIST-1e doesn't possess a thick hydrogen-rich atmosphere like newly formed gas giants. If it ever had such an atmosphere, radiation from its active red dwarf star has stripped it away. This isn't surprising. Red dwarf stars are violent, especially when young. They emit powerful flares that can blast away atmospheric gases over millions of years. The inner planets of TRAPPIST-1 have been subjected to this radiation for billions of years. But Earth-like planets can build secondary atmospheres. Volcanic eruptions pump gases from planetary interiors. Outgassing releases trapped volatiles. Our own world lost its primordial atmosphere and constructed a new one over time. The Webb data hint that TRAPPIST-1e might have done the same. Researchers detected possible signatures consistent with a nitrogen-rich atmosphere, containing traces of methane. Such a composition would resemble Saturn's moon Titan, a world with thick haze layers. However, the detection isn't definitive. The star TRAPPIST-1 is extremely active, with surface features that contaminate the spectra astronomers are trying to measure. Separating planetary signals from stellar noise requires extraordinary precision and extensive observations. Additional observations are already scheduled. 15 more transit measurements. Astronomers hope to build enough statistical confidence to distinguish real atmospheric features from noise. If successful, the detection would represent a historic achievement, the first confirmed atmosphere on a potentially habitable world beyond our solar system, a target for future observations searching for biosignatures, the chemical fingerprints of life. One researcher described the work as pushing the limits of what the telescope was designed to do. Webb was conceived before the TRAPPIST-1 system was even discovered. That it can study these worlds at all is remarkable. The search continues. Each transit provides more data. Each analysis refines our understanding. Somewhere in the noise may lie evidence that changes everything we believe about our place in the universe. But let's bring our journey closer to home now, because Webb has revealed something remarkable not just about distant worlds, but about how stars and planets are born right here in our own galactic neighborhood. Let yourself sink even deeper into comfort. Let your muscles go completely loose. And listen as I tell you about stellar nurseries, the cosmic cradles where new stars ignite. Some images transcend their scientific purpose and become icons. They capture human imagination in ways that statistics and data never can. In 1995, the Hubble Space Telescope captured such an image. Towering columns of gas and dust, backlit by the glow of newborn stars, rising like cathedral spires against the darkness of space, the pillars of creation. For nearly 3 decades, this image shaped how humanity visualized cosmic birth. Countless textbooks reproduced it. Museum visitors stood transfixed. The pillars became synonymous with the wonder of space exploration. Then the James Webb Space Telescope looked again, and what it revealed transformed our understanding. The pillars sit within the Eagle Nebula, roughly 6,500 light-years from Earth. Each column stretches several light-years tall. These are structures of almost incomprehensible size. Hubble showed us their beauty. Webb showed us their violence. In near-infrared light, the telescope pierced the dusty exteriors that had hidden the pillars' interiors from view. Suddenly, astronomers could see deep inside the columns, and what they found was chaos. Newborn stars by the hundreds, fiery jets blasting outward at supersonic speeds, shock waves rippling through the gas. The pillars aren't peaceful nurseries. They're battlegrounds where gravity wages war against radiation, and new stars claw their way into existence. Close your eyes. Let the image form in your mind. Towering pillars of cosmic dust, glowing at their edges, and within them, hidden lights. Stars being born in violence and beauty. A research team studying Webb's data identified 153 young stellar object candidates. Within the pillars, these are protostars, objects still gathering mass from their surroundings. Some only a few 100,000 years old, cosmic infants by any measure. But the most striking finding was where these infant stars cluster. They concentrate along the edges of the pillars, not randomly distributed throughout, and their ages appear to decrease with distance from the massive stars illuminating the nebula. This pattern tells a story. The intense radiation from nearby mature stars is sculpting the pillars, eroding them like wind carving sandstone. But as the radiation compresses the gas at the pillar edges, it also triggers gravitational collapse. The pillars are being destroyed, and their destruction is creating new stars. This process, Hall-triggered star formation had been theorized for decades but never observed so clearly. Webb's data show it happening in real time. The wavy patterns along the pillar edges that look like glowing lava flows aren't decoration. They're supersonic jets from newborn stars smashing into the surrounding gas. Each collision creates bow shocks, rippling patterns of heated material that trace the violence of stellar birth. One researcher described the images as practically pulsing with activity. These young stars are announcing their arrival with spectacular violence, but there's tragedy hidden in this beauty. The same radiation triggering new star formation is also dooming the pillars themselves. Eventually, the columns will be completely eroded away. Their constituent gas will disperse into space. The stars they spawned will drift apart. The pillars of creation are temporary structures, monuments to a moment in cosmic evolution that will pass. In perhaps 100,000 years, they'll be gone entirely. We are fortunate to witness them while they still stand. Let your breathing slow even further. Feel your body becoming heavier, sinking deeper into the mattress. The weight of gravity, the same force that creates stars, gently holding you. Webb has captured another iconic stellar nursery, the cosmic cliffs. This image shows a region within the Carina Nebula, roughly 7,600 light-years from Earth. What appears to be a landscape of mountains and valleys is actually the edge of a massive stellar nursery. The cliff face marks the boundary between denser gas where stars form and the cleared cavity carved by radiation from mature stars. Previous telescopes could see the cliff itself, but couldn't penetrate it. Webb's infrared vision changed everything. Behind the curtain of dust, the telescope revealed protostars still gathering mass, objects that had never been observed before, wrapped in shrouds that blocked visible light but allowed infrared wavelengths to escape. Each glowing point marks a star in the process of being born. The image also captured jets and outflows from these hidden babies, streams of material ejected at high speeds, colliding with surrounding gas, creating patterns that trace the violence of stellar formation. But the cosmic cliffs did more than reveal hidden stars. They demonstrated the interplay between destruction and creation that drives cosmic evolution. The radiation from nearby mature stars is eroding the cliff face. Gas boils away under intense bombardment. Over millions of years, the cliff will retreat, exposing more of the dense gas behind it. As the erosion proceeds, it compresses gas at the boundary. This compression triggers gravitational collapse. New stars form precisely because the cliff is being destroyed. Destruction enables creation. The same process operates in the pillars of creation and countless other stellar nurseries across the galaxy. Radiation from one generation of stars seeds the formation of the next. Picture this cycle. Stars being born, living their lives, dying in brilliant supernovae or fading gently into darkness. And from their remains, enriched with heavy elements, new stars rising, new planets forming, new opportunities for complexity, for chemistry, for perhaps even life. The cycle continues, has continued for billions of years, will continue for billions more. You are made of this process. The atoms in your body were forged in ancient stars. The calcium in your bones, the iron in your blood, the oxygen you're breathing right now, all created in stellar furnaces and scattered into space when those stars died. You are stardust, contemplating stardust, the universe experiencing itself. Let that thought settle gently as your breathing slows even more. You are connected to everything, to distant nebulae, to ancient stars, to the cosmic cycle of birth and death and rebirth. And Webb has revealed one more beautiful aspect of star formation. In a nebula called the Serpens Nebula, roughly 1,300 light-years from Earth, astronomers discovered something remarkable: a group of protostellar outflows, jets of gas blasting from newborn stars, all pointed in the same direction. Typically, such jets have varied orientations. Each star should have its own random rotation axis. Seeing multiple jets slanted the same way suggested something deeper. These aligned outflows are like sleet pouring down during a storm, one researcher explained. They provide a historical record of how stars are born. Young stars shoot supersonic jets from their poles as they gather mass. The direction of each jet reveals the rotation axis of its source star. In the Serpens Nebula, a cluster of particularly young stars, some only about 100,000 years old, all share similar rotation orientations. They inherited their spins from the collapsing cloud that formed them. Angular momentum conserved across the formation process, a prediction of physics now confirmed by observation. Everything follows rules. The universe plays by consistent principles, and those principles are becoming clearer with each image the telescope returns. Let yourself relax completely now. Every muscle loose, every breath slow and deep. We're approaching the end of our journey, but there are still a few more wonders to share. While Webb explores the distant universe, ancient galaxies and far-off worlds, it has also turned its golden eye toward our own cosmic neighborhood. And even here, close to home, it has revealed surprises. Let me tell you about Neptune, the most distant major planet in our solar system, and a mystery that persisted for 30 years, for 3 decades. Astronomers searched for auroras on Neptune. They knew auroras should exist there. Every other giant planet displayed them. Jupiter's auroras blaze hundreds of times brighter than Earth's. Saturn wears luminous halos around its poles. Even distant Uranus glows with faint northern and southern lights. But Neptune refused to reveal its secret. When Voyager flew past the ice giant in 1989, instruments detected tantalizing hints of auroral activity. But the technology of that era couldn't confirm what was happening. Ground-based telescopes tried for decades afterward. Nothing definitive emerged. The problem was distance. Neptune orbits 30 times farther from the Sun than Earth does. At such vast separation, the faint glow of an aurora is extremely difficult to detect. Then the James Webb Space Telescope took its turn. In June 2023, astronomers directed Webb's near-infrared spectrograph toward Neptune. They were originally planning to study the planet's atmospheric circulation. What they found instead astonished them: clear, unmistakable auroras, glowing cyan splotches of light high in Neptune's upper atmosphere. The first confirmed detection of auroral activity on the solar system's most distant major planet. One researcher who had spent years searching for this signal described being stunned by the detail and clarity. After decades of failure, the discovery came almost casually during observations intended for different purposes entirely. But the auroras themselves presented immediate puzzles. On Earth, auroras cluster around the magnetic poles. Charged particles from the Sun spiral along magnetic field lines and strike the upper atmosphere near the Arctic and Antarctic. Neptune's auroras appear nowhere near its poles. They glow at mid-latitudes, the planetary equivalent of South America or Southern Africa. This bizarre location results from Neptune's extremely tilted magnetic field, which is offset by 47 degrees from the planet's rotation axis. The planet's magnetic and geographic personalities are entirely disconnected. Why Neptune's magnetic field is so misaligned remains unclear. The planet rotates on an axis tilted only 28 degrees from vertical, nearly identical to Earth's axial tilt, but its magnetic field points in a completely different direction. Let your mind rest gently on this mystery. A distant world, cold and blue, where auroras dance not at the poles but at mid-latitudes, where magnetic fields twist in unexpected directions, where even after centuries of observation, surprises remain. Webb also revealed that Neptune's upper atmosphere has cooled dramatically since Voyager flew past, several hundred degrees colder than measurements from 1989 suggested. This dramatic cooling may explain why the auroras remained hidden for so long. The planet sits so far from the Sun that seasonal changes unfold over decades, where the patterns may shift on timescales longer than human careers. We're only beginning to understand the rhythms of these distant worlds. Closer to home, Webb has revealed the most detailed view ever captured of a supernova remnant in our own galaxy. Let me tell you about Cassiopeia, the youngest known supernova remnant in the Milky Way. 340 years ago, a star exploded. The light from that catastrophic death reached Earth sometime in the late 1600s, though no contemporary observers recorded seeing anything unusual. Today we call the expanding shell of debris Cassiopeia a dot at 11,000 light-years away. It remains a laboratory for understanding how massive stars die. Previous observations revealed Cassiopeia A as a roughly circular bubble of hot gas. Hubble showed intricate knots and filaments. But Webb's infrared vision uncovered something entirely new. Deep within the remnant lies a structure no one had seen before. A thick sheet of material pockmarked with dozens of small, nearly circular holes. Because of its green appearance in representative color images, astronomers nicknamed it the Green Monster. The discovery was completely unexpected. Supernova remnants are supposed to be hollow shells, the outer skins of exploded stars racing outward into space. What is the Green Monster? And where did those holes come from? Detailed analysis suggests it's circumstellar material, gas and dust shed by the star before it exploded, now illuminated and sculpted by the blast wave that followed. The holes appear to be puncture wounds, knots of high-velocity ejecta, chunks of the exploded star racing outward at thousands of kilometers per second, have punched through the sheet like bullets through fabric. Picture this: the explosion sending debris outward at incredible speeds, some pieces overtaking others, faster fragments catching up to slower material shed earlier, and where they meet, collisions, penetrations, holes torn in cosmic fabric. The research team measured more than 24 of these circular structures. Each spans a distance that, if our sun were placed at the center of one hole, its boundary would lie near the inner edge of our solar system's Oort cloud. Webb also detected remarkably bright carbon monoxide emission. This molecule forms in the cooling debris of supernovae but had never been observed. At such high temperatures, chemistry in action amid the chaos of stellar death. Supernovae matter to all of us personally. They created the heavy elements that make up our bodies. Understanding how stars die is understanding our own origin story. Let your breathing deepen. Feel yourself drifting. We're near the end of our journey now. Just a few more stops. A few more wonders to witness before we let you slip completely into sleep. As we drift toward the end of our cosmic journey, let's reflect on what all these discoveries mean. Not just the individual facts, the distant galaxies, the strange planets, the runaway black holes, but the larger picture they paint. The James Webb Space Telescope has fundamentally challenged our understanding of the universe. Not in small ways, not with minor corrections, but with revolutionary observations that force us to reconsider basic assumptions about how the cosmos evolved. The early universe was not primitive. It was sophisticated, organized, capable of assembling massive structures far faster than our models predicted. Galaxies appeared too soon, too bright, too mature. Black holes grew too massive too quickly. Spiral structures emerged billions of years before they should have. Chemical enrichment happened almost immediately. Either something accelerated cosmic evolution in ways we don't understand, or our models are missing fundamental physics. The expansion of the universe presents its own puzzle. Different measurement methods give different answers for how fast space is expanding. The discrepancy persists despite decades of refinement. Webb has confirmed the problem is real. Dark energy, that mysterious force accelerating the expansion, might not be constant after all. It might have been stronger in the past and is gradually weakening. If true, the future of the universe is far more uncertain than we believed. These aren't separate puzzles. They're connected. The impossible early galaxies, the Hubble tension, the variable dark energy. They're all symptoms of something deeper, something missing from our understanding. Some researchers believe early dark energy might unify several mysteries. Others propose modifications to dark matter. Still others wonder if general relativity itself needs revision on cosmological scales. No one knows yet. The data continue accumulating. The debates continue. And that's exactly how science should work. Let your breathing slow as you contemplate this. The greatest minds in physics and astronomy, equipped with the most powerful telescope ever built, are discovering that reality is stranger than our best theories predicted. This should excite us, not discourage us. The best moments in science come when observations outrun explanation, when nature reveals itself to be richer than our models captured, when we must return to first principles and think again. We're living through such a moment. The telescope 1 million miles from Earth has shattered comfortable assumptions. The cosmos isn't what we thought, but now we know what questions to ask. We know where the mysteries lie. We have clues pointing toward deeper truths and beyond the grand cosmological questions. Webb has expanded our understanding of worlds. It has found planets unlike any we imagined. Diamond rain worlds, lava planets with atmospheres that shouldn't exist, potentially habitable worlds orbiting dim red stars. It has captured stellar nurseries in unprecedented detail, showing us the violent beauty of star formation. It has revealed the youngest supernova remnant in our galaxy as never before seen. It has confirmed auroras on Neptune after decades of searching. Each discovery is a thread, and together these threads weave a tapestry, a new picture of the universe, richer, stranger, more wonderful than the old one. But here's what I find most beautiful. With all we've learned, with all Webb has revealed, the universe remains fundamentally mysterious. We've answered some questions and uncovered dozens more. For every door Webb opens, we find 3 more doors behind it. The search for life continues. Each observation of an exoplanet atmosphere brings us closer to answering humanity's oldest question. Are we alone? TRAPPIST-1e awaits further study. K2-18b sparks debate. Somewhere out there, on a world we haven't even discovered yet, might exist the first confirmed signs of life beyond Earth. The nature of dark energy remains unknown, whether it's constant or variable, whether it will lead to a big freeze, big crunch, or big rip. These questions about the ultimate fate of everything remain open. The formation of the first stars and black holes, the mechanisms that assembled the first galaxies, the reason why structure formed so quickly. These mysteries persist, and that's wonderful, because mystery is what drives discovery. Wonder is what propels science forward. Not knowing is the beginning of knowing. You're alive during this extraordinary time. You're here to witness these discoveries. Future generations will read about this era in history books. The time when humanity first peered back to cosmic dawn. The time when we seriously began searching for life on other worlds. The time when our models of the universe were challenged and revised. You're part of this moment. By learning about these discoveries, by feeling wonder at the cosmos, you're participating in humanity's grandest adventure, the quest to understand where we came from, where we're going, and whether we're alone. Let yourself feel grateful for this, for consciousness, for curiosity, for the ability to wonder about galaxies billions of light years away while lying comfortably in your bed on this small planet we call home. The universe is vast, ancient, filled with wonders we're only beginning to discover. And you are made of this universe. You are stardust that has become conscious, atoms that once swirled in stellar furnaces, now organized into the remarkable structure that is you. Tomorrow, the universe will still be out there, vast, mysterious, filled with secrets waiting to be uncovered. The James Webb Space Telescope will continue its silent vigil, observing, measuring, revealing. But for now, you can rest, you can sleep, you can let your mind drift among the stars, knowing that you're part of something infinitely larger than yourself. Thank you for taking this journey with me. Thank you for letting me share these stories of cosmic wonder. I hope you found peace, relaxation, and perhaps even inspiration. If you enjoyed this voyage through the universe, please remember to like this video. Subscribe to Sleepy Science Tales for more peaceful explorations of science and the cosmos. And share this with someone who might need help falling asleep, or who simply loves learning about the universe. Your support means everything. Every like, every subscription, every share tells me these stories matter. That science matters. That wonder matters. And now, as we approach the final moments of our journey, let me guide you into the deepest relaxation, the gentlest transition into sleep. Let your breathing become even slower now, even deeper. So slow and deep that each breath feels like a gentle wave, washing through your body, carrying away any remaining tension. Imagine yourself floating, not in space this time, but somewhere peaceful, somewhere safe, somewhere perfectly suited to your rest. Maybe you're floating on calm water, the gentlest lake, barely any movement, just the softest rocking, like being cradled, held safely, supported completely. Or perhaps you're drifting on a cloud, impossibly soft, impossibly comfortable, suspended in twilight, not day, not night, but that perfect in-between time when the world grows quiet. Or maybe you're simply here, in your bed, feeling the mattress support your entire body, the pillow cradling your head, the blankets providing just the right warmth, everything exactly as it should be. Whatever image brings you comfort, rest there now. The universe we've explored tonight, the ancient galaxies, the impossible black holes, the strange new worlds, they all exist in the same cosmos that contains you. The same fundamental forces that shaped galaxies also shaped you. The same atoms forged in dying stars are the atoms that make up your body. You are not separate from the universe. You are an expression of it, a way for the cosmos to know itself, to wonder at itself, to feel awe at its own existence. And right now, in this moment, the universe, through you, is resting, preparing for sleep, allowing the body to restore itself, permitting consciousness to drift into dreams. There is nowhere else you need to be, nothing else you need to do, no problem that requires solving right now. The universe has existed for 13.8 billion years. Your concerns can wait until morning. Feel your body becoming heavier, sinking deeper into the mattress, as if gravity is gently pulling you down into the most comfortable rest. Your breath, so slow now, so steady, like the patient rhythm of the cosmos itself, expansion and contraction, breathing in and breathing out, the fundamental rhythm of existence. The stars we talked about tonight, they're still shining, the galaxies are still spinning, the black holes are still consuming, the universe is still expanding, and all of it continues whether you're awake or asleep. So you can let go now, you can release your grip on consciousness. The universe will keep running without your attention. Everything will still be there when you wake. Let your thoughts drift apart, like stars separating in an expanding universe, each thought moving away from the others, more space between them, until eventually, there's only peaceful emptiness, the quiet void, the gentle darkness, your eyelids, so heavy now, if they're not already closed. Letting them close feels like the most natural thing, the most effortless thing, just letting them fall, and you're breathing, continuing its steady rhythm. But you don't need to pay attention anymore. Your body knows how to breathe. It will continue breathing while you sleep, while you dream, while you rest, the weight of sleep, settling over you like stardust, gentle, peaceful, irresistible. Somewhere in the distant cosmos, light from ancient galaxies continues its journey through space, crossing billions of light years, some of it arriving at Earth just as you close your eyes. Photons that began their journey when the universe was young, finally completing their voyage, just as you complete yours. From waking to sleeping, let go, drift, sleep, you are safe, you are comfortable, you are exactly where you need to be. The universe holds you in its vastness. The Earth supports you with its gravity. Your bed cradles you with its softness. Sleep now, peaceful cosmic traveler. Rest among the stars and dream of wonders. Good night.